In our previous video, we introduced semantic networks, and demonstrated two common search methods in a network that represented the relationships between employees at a small office. Let us now take this concept further, and explore how we can construct a knowledge graph from text. Here's a random excerpt from a lecture that was given a few years ago in a vertical takeoff and landing aircraft design conference. Imagine that in the audience we had a robot who heard all the lectures, processed them and came back with all the additional knowledge it had gained from the conference. But not only that, on its way home from the conference, it managed to connect all that new knowledge to everything it already knew in the field of aeronautics. As for the short excerpt, don't worry about reading it all. Even from the first sentence, we can already see that this section discusses the main factors that enable vertical takeoff. And remember, this could have been a lecture on any topic. Everything that we will show in this video is equally applicable to any desired domain. The first thing we want to do is take the knowledge embedded in this text, and reconstruct it in a way that allows us not just to search for keywords, which is easy, but to ask questions and receive answers that truly reflect the knowledge conveyed in the lecture. This might sound almost like fantasy. After all, doesn't the computer need to understand what's being said? Well, it depends on our interpretation of understanding. If understanding means being able to associate newly acquired knowledge with all of our previous knowledge, then yes. What we're about to do will certainly go halfway towards that goal. Before we start, let's make a heuristic assumption. We can't prove it right now, so we hope viewers will find it easy to accept. We are proposing that key concepts, or keywords like lift, air velocity, rotors, etc., are closer to each other in the text, in terms of word count, the more they are related in real life. Conversely, if they're not directly related, you'll find them separated by several sentences or even in different parts of the lecture. Maybe even in different lectures altogether. Sounds logical, doesn't it? Let's try and see where it gets us. Here are, highlighted in color, some of the concepts, mostly nouns, that are mentioned in this section. We call these terms. Between them, we can find verbs that connect these terms, which we will call relations. Please note that here, we are building a knowledge graph from text manually. This is done intentionally to demonstrate the process. Computers accomplish this today with little or no human input. Recognizing the terms and relations inside any sort of text is a fundamental concept in language processing. Terms and relations are the building blocks of natural language processing, NLP. We will soon see that once a knowledge graph has been created from this text, the terms inside the text have become the graph's nodes. The relations, on the other hand, end up as the names attached to the graph's edges. The task of sorting out the terms has its own acronym in AI, NER, meaning named entity recognition. And the whole process of breaking up the text into its building blocks is termed IE, meaning information extraction. Now, we remember our heuristic assumption that the closer two terms are to each other in the text, the closer they are in real life. So let us look at the distances, in word count units, between the key terms in this text. We have shown just a few paths. To complete this, we must count the distances between each one of the terms, and all the other terms. Now, unless the text is very short, multiple occurrences will surely appear between any two terms in a given text. The rule here is to take the smallest distance, for each specific pair. It's time to draw our graph. There are of course infinite ways to place the terms, which will become nodes, on the screen, and connect them with edges. Here, we will try to place the terms in a manner that correlates with their relative word count distance in the text. So let us draw concentric circles around each term with radii denoting distances from other terms, and move the terms around, together with their concentric circles. We will move them around until we find an arrangement where the mutual distances between all of the terms on the screen are close to their word count separation in the text. This is a geometrical problem that the computer knows how to solve iteratively. By the way, genetic algorithms are ideal for this task. The iterations go on until it obtains a good result. Again, for this video we did this manually, moving the different terms around the screen until their mutual distances were close to what we measured on the original text. Now, we no longer need the guiding circles, and it is time to draw edges between the terms, reflecting the parts of the text that connected the various terms to each other. So far, guided by our heuristics, the concepts have fallen into place, based on their mutual distances in the text. Surprisingly, we notice on the screen two slightly different groups. The terms in left group are more related to physics. You can find there, mass flow rate, induced air velocity, rotor disk area, and acceleration of air. At the bottom right area we see mostly terms related to mechanics and the machine itself. These include aircraft, takeoff, weight, power, rotors and thrust. It is amazing to realize that we did not create these two zones deliberately, it is just something that happened. Let us now complete this network by adding names to the edges to reflect their meanings. When done automatically by computers, the edges are extracted as relations, and pasted over edges that connect adjacent terms in the text. Now that we've constructed our knowledge graph, let's ask it some questions and see if the structure of the graph provides the ability to get complete and unambiguous answers to our questions. Question: what's the connection between disk area and V induced? Answer: they are both elements in the mass flow rate. Question: how are weight and thrust related? Answer: they both affect the power. Question: how is V induced produced? Answer: V induced is produced through the acceleration of air, affected by low pressure, created by lift rotors. Now, imagine that we already had one network in our database. And suppose that it was related in some way to one or more of the terms we extracted from our section. Then, even if just one node in each of the two networks had the same name, a computer that has just received our network would merge these two nodes into one. This would immediately create a link between the two separate graphs, and it would unify searches initiated on any of the networks, essentially making them into one. Taking the above one step further, if our initial lecture, with its representation as a knowledge graph, had common features with other knowledge graphs that are already linked in our database, then every time that we would have a new graph to upload, it would expand our overall knowledge graph more and more. If this continues, lecture after lecture, papers of whole conferences, manuals and books, each with their own knowledge graph, then after a while, we will have created an enormous knowledge graph that encompasses perhaps all of current human knowledge in our domain. This is exactly the way by which current large knowledge graphs in the fields of biology, semantics, pharma, medicine, and chemistry, to name a few, have evolved. Scientists expect that in a decade, all of the knowledge in the internet will already have been converted into knowledge graphs. This is one of the directions in which AI is headed.